Hi, and welcome to 13.1 Wave Properties. Unit 13, Waves. Very important unit. Kind of different from what we've done in the past, but some things are going to come back, like speed. We talk about wave speed in future lessons. So Unit 13 is all about the properties of waves in general. Unit 14 is more specifically about sound waves. And then Unit 15 is about electromagnetic waves, such as like visible light, which is kind of cool, and reflection and refraction. So waves is going to take us pretty much to the end of the year. So Unit 13 is very important because it kind of just gives you all the vocabulary so that you know the parts of a wave and how they interact. And then we'll do specific examples of different types of waves, such as sound waves and electromagnetic waves. So without further ado, let's do this. Well, I do want to say one disclaimer. So typically I do period and frequency first, and then I do wave properties because I like talking about simple harmonic motion, and then I start doing waves. But all the lecture videos I found for this topic were talking about waves first, and then they use waves to talk about period and frequency. So these are a little bit flipped in the future, in case you're wondering why this is called 13.1 and not 13.2. Anyway, number one, which letter shows the crest of a wave? So the crest is kind of like the top of the wave. Have you ever brushed your teeth before? Maybe. So you know what's the symbol for the crest symbol, right? If you had Crest toothpaste, it's got this nice little, the peak there, or the crest of the mountain, or whatever else. So it's the top of the wave. So letter E is showing the crest of the wave. And which letter shows the trough of a wave? So that word is trough. And have you ever seen a pig before? Little pig here with the little pig. What do pigs eat out of? What is this pig gonna eat out of here? Pigs eat out of a trough. Nom, 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 nom. So all the food that the pig is gonna eat, just bloody No, I'm just kidding. That's not blood. It's nice vegetables that the pig's gonna eat. Okay, so the pig's gonna eat out of this trough. Okay, so it's the bottom of the wave. That's point G. Kind of a weird looking G. It's like a G. I make my G's like that. I don't know why. The wavelength. Okay. So wavelength is the length of the wave. How long is the wave? Is it super stretched out? Is it like a long wave? Or is the length of the wave super short? So this is the wavelength here. And what do they use to represent wavelength? Wavelength is represented by this. Anybody know? What is this thing called? What's that Greek letter called? Is this going to help you? There's a little hint. Did that help you? Anybody know what this is called? It's a lambda. Get it? Lambda. Lambda is the Greek letter that looks like that. Oh, that. Oh, kind of like that. So a lambda is what they use to represent wavelength. And the way you do that is just draw, like, if this is you remember grade school and you draw dot 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 dot. All right, so the grade school drawing letters, you draw a diagonal down and then in the middle, just like that. So that's called wavelength. It's the length of the wave. And how do you measure wavelength? I mean, this is the big long wave, right? The whole thing? No. You got to measure it from one point in the wave to the next consecutive point that's in phase there. So it starts, if we're looking, let's start somewhere simple. So start in the beginning. Here's the crest. All right, so this is the next point that goes through equilibrium. Does that mean that this is the length of the wave? Well, I have the crest here, but isn't there also a trough involved in a wave? So you also have to do the trough. So we have the crest and the trough, and now we're back to our starting point. Crest, trough, starting point, crest, and then that. So that's a half wavelength at the end. So I'll erase this. And yes, we can say from this point so crest, trough, this is a full wave. That's what a full wave looks like right there. And then you could even draw like this. This is used to show this is the length of the wave, the wavelength, okay, lambda. But that's not one of the choices because you have to do between which two letters. So let's start with letter. Oh, there's that nice message. A is definitely not going to be the wavelength because it's going in the opposite direction. We'll talk about that when we do amplitude. How about from B? Okay, B, there's the trough. That's a half wavelength. You got to get the crest in there. So from B to F, that is one full wavelength. Is there another valid option? Well, C again is pointing in the wrong direction. That has to do with amplitude. How about if we go from D? D, there's the crest. And that's not F, that's half a wavelength. You need also the trough in there, but there's no letter over here. And as you see, there's no letters past that, so you can't even do. What about E? So can you draw a wavelength? If E was here, F, G, H would be here, I, like, is this the wavelength? Yes, that is the same length as going from here to here. This distance is the same. So the definition of the wavelength is technically from one point on the wave to the next consecutive point that's in phase with that one. So from B to F, that's also the wavelength right there. All right. Okay. So you could go crest to crest. You could also go trough to trough. A lot of different ways to look at the wavelength. Alrighty. Number 4 says, how many complete waves are shown in the diagram? So now ignore all the letters and stuff. Let's just start here like we did before. Crest, trough. This is one wave. Crest, trough. This is a second wave. So we'll draw like this. Second wave number 2. Now we just have from here, we have the crest and nothing else. So this, you see how this is like half? So this is 2 point, I'm going to write it differently. I'll write it like, this is one wave, this is one wave, and this is half a wave. Okay, so what's the total? 2.5, 2.5 waves. That's a W, okay. All right, now the amplitude. In a mechanical wave, which mechanical waves are waves that require a medium to travel through. A medium could be like water. Could you have a water wave without water? No, you need to have the water there to have a water wave. So the wave in the water, the medium through which that wave is traveling is the water. All right, so a mechanical wave is what we're talking about with these. The amplitude shows the amount of energy that's in that wave. Is it like a little ripple in the water, or is it a huge tall wave? The huge tall wave has more energy. It took more energy to make that wave than maybe a tiny little rock falling in the water. All right, so was it a tsunami caused by an earthquake and a lot of rocks falling in the water, or was it a rocks moving around under the ocean, or it was just a tiny little pebble that was dropped into the water? So the amplitude shows the amount of energy that's in the wave. Now, when you're thinking about water and the medium, if there were no waves, this is what they call the equilibrium position. So if you're going to measure how much energy there was, you say, okay, I took that blue line, this is what the calm water, but now it's being displaced this far. And from at this point, it's being displaced this far from the equilibrium position. So the amplitude is always drawn from equilibrium. It's always measured from, this was my original state. I was displaced this far away from the equilibrium. So as you could see, you're looking for the arrow that's just here. C is the correct answer. Why is A the incorrect answer? That's actually twice the amplitude. You have the amplitude of the crest and the amplitude of the trough. That's not correct. That's not the correct way to draw the amplitude. We're looking for from equilibrium to the maximum displacement. So this is also the amplitude. This is also the amplitude. It's always drawn from the equilibrium position. So let me erase this other mess. Okay. Okay. All right, so that's what we're looking at. Choice C. Choice C, that's the amplitude. All right. Is this longitudinal or transverse wave? So the video that was posted kind of talks about the difference between longitudinal and transverse. I have a couple PowerPoint slides that show the difference. So let's take a look at those.
Okay, so for longitudinal waves, the particles travel parallel to the velocity of the wave. Let's see if, I don't know why this GIF isn't working here. What the heck?
There we go. Okay. So this is showing, take a look at this gray thing moving. All right. And these are all, you could think of them as maybe air molecules or water molecules, or even like people in a wave pool seen from the top. You ever been in like one of those wave pools before at a water park or something? So this is moving back and forth, and it pushes the particles together. So you could see the wave is moving across. See these like waves of compressions moving across to the right? Well, if you focus on just one little person in the wave pool or air molecule, if you just focus on this one red dot, you could see the dot's actually just moving back and forth. It doesn't travel with the wave. So waves transfer energy. So you can see the energy moving across, but they don't transfer matter. The matter stays in its same position. So the longitudinal waves, the particles travel parallel to the velocity of the wave. That means that the particles move along, like longitudinal, they move along the direction of the wave propagation. So the particles are moving back and forth in this direction. And what direction are the waves traveling? Point with your finger. So the waves should be traveling to the right. You see how they're parallel to each other? In longitudinal waves, the particle vibration is parallel to the wave direction. Okay? One way you could remember that is by looking at the word. See this L? It kind of looks like this gray thing, right? So what we're going to do is we're going to have a fancy animation, and the L is going to push these like they are the particles in that little diagram. Whoa, longitudinal, like that. See, it's like bouncing between the two things. Fancy stuff. Very nice. Okay, what about transverse waves? In transverse waves, the particles travel perpendicular to the velocity of the wave. What direction is the wave traveling here? You see the crest? Focus on the crests. The crests are moving to the right. But if you focused on one little dot, what direction is the dot going? The dot is going up and down. So the wave is going to the right, the dot is going up and down. Those two directions are perpendicular to each other. So the dots are going up and down like that, and the wave comes along, boom, 90 degrees. Those are perpendicular. That's a transverse wave. Transverse can be remembered by looking at the S's. Longitudinal, there's no S. But in a transverse wave, you just look at the word. That's going to remind you that the S goes up and down. There's the trough and the crest there. All right, so that's kind of reminding you what they look like that. Very nice. Wow. What a great way to remember that stuff. All right, back to the assignment. So is this a longitudinal or transverse wave? Remember, these little S's are hints. See, like the S, transverse. It's a transverse wave, transverse. Okay, so that's like the basic overview of the parts of the wave and types of waves. Number 7, is the wave moving to the right? If the wave is moving to the right, what direction will point B travel in the next instant? Draw an arrow on the diagram to show this movement. So here's our wave. Okay, let's picture it as a water wave. It's moving along. Let's see if I could use this. Here's point B. Okay, point B. So I guess we'll draw it like on the wave to help visualize it. All right. I'm going to try to move. Let's see if I can do this. Okay. So the wave is moving to the right. What direction is B going to be forced to go? So let's slow. If I move it to the right, it's man. I was hoping that. Okay. As I move it to the right, point B has to go. It's like following. I have to do it like piecemeal here. See, now point B's got to stay in the same location here. Like it has to stay in the same line. It can't move. The wave isn't moving the matter. Okay? It's moving the energy. So B has to stay on this line. Let's draw the line that it has to stay on. Okay? Has to stay on this line. And when I move the wave gets to move like the energy is moving. But point B, if you're hanging out on this water wave, you're going to feel like you got moved up and down. Oh, this has to be set to the back. What if I flatten it? I think that's there forever now, but that's okay. All right, and then this moves over. B has to stay in that same line. What a great way to do this, Mr. Dangle. All right, and then moves across. Still like kind of. All right, now we're past the crest. Point B gets to go back down a little bit. Doesn't help that I'm moving the wave up and down too. It should just be moving to the right. Man, very, very clear explanation of this weird question. I don't know why the Regents likes to ask this question, because you really have to visualize the wave moving across the page. And it's kind of hard to do that. It tricks a lot of kiddos. So if you're confused, is like, I thought it was going to go down. It looks like it's going downhill. Look at point B. Point B is right here. Doesn't point B want to travel like go that way? No. You have to visualize the wave moving across. And as it goes across, point B has to stay on this line, and it's being forced up above the wave. So it goes up. That's the answer. Point B has to go upward. Oh boy. Here we go. Get out of this. Boom. Shaka laka. Okay. Point B is traveling upward. Up. Cool. Number 8. Why can't you calculate the frequency of the wave in the diagram? What information is missing? Topic 13.2. So at the beginning of the video here, I said that normally I do these lessons in a different order, and you know what frequency is first. But in the next lesson, we'll talk about that. So why can't you calculate the frequency in the diagram? You don't know how much time for one cycle. In other words, what is the period? And the period is a capital T. I think we did period before when we did circular motion. It's like the time it takes for one revolution. Well, this is how much time does it take for the wave to pass by you. So the wave is moving. One full wave passes by you in this many seconds. That's going to be the period. Don't worry, though. Like, the next lesson is all about frequency and period. It's just unfortunate that we had to do it out of order this year. So don't worry about that question for now. You can come back to it. Same with number 9. What is frequency? Describe it in your own words. I could give you a little sneak preview. It's the inverse of the period. That's like the mathematical definition. That's all you have to know in terms of like calculating stuff. You just do 1 over the period. But in your own words, what is frequency? And again, this is just a sneak preview. We go for it in more detail in the next lesson. But in case you're wondering, I like to say frequency describes how frequently the waves pass by every second. Or you could just say how frequently the waves pass by. So how frequently do the waves pass by you? Frequency describes how frequently the waves pass. I like to use the word in the definition here because you've probably heard the word frequently before. Like how many times? You could say how many times per second, and that's what it is. So how many waves? How many waves per second? Per second. And if you look back at the formula I just wrote, 1 over the period, remember the period is measured in seconds. It's the time, the period is the time for one cycle, And if you do that, you get 1 over seconds. How many waves per second? So then 1 over seconds turns into hertz. The unit is hertz. So I just kind of like went over that super quickly, but they go into it more detail in 13.2. How many waves per second? How frequently does it go by? Okay, and then you measure it in terms of hertz or inverse seconds, but nobody wants to do inverse seconds. They say hertz. Okay, anyway, what does amplitude measure? So we said amplitude was the distance that you're displaced from equilibrium, and it's a way to measure how much energy is in the wave. So amplitude measures the energy of the wave. And are sound waves transverse waves or longitudinal waves? Very, very good question. And why do you think so? So again, Unit 14 is going to be all about sound, but if you had to guess, are sound waves transverse waves or longitudinal waves? And I think it did say it in that instructional video that was posted. What do you think? Do they look more like these? So are sound waves more like this? And what exactly is sound? Or are sound waves more like transverse waves? So is this what sound looks like? Well, you have to know what exactly is sound. And again, we talk about it in Unit 14, but sound is actually a longitudinal wave. So let's go back to that slide. Let's see if we could get there. Here it is. Okay, so the air molecules in the room that you're in right now look closer to these molecules, where the speaker in your screen or the speaker in your device has a little diaphragm that's moving back and forth, and it's literally pushing the air molecules back and forth just like these. And that pushing continues through there. It propagates through the air. So this is like a column of air, or the air that's in your room right now, or the air between the speaker and your earbuds. If you're wearing earbuds, there's a little air in your ear there, and the air vibrating like this comes in and it hits your eardrum, which forces your eardrum to move back and forth, which is kind of cool. So sound is a longitudinal wave. And if you're wondering, how does my eardrum moving tell my brain that there's a sound there? Like, where is the connection there? We talk about that a little bit in Unit 14. So sound is a longitudinal wave. And the thing is, you need a medium. So in the example you just said, these little particles are air molecules. The air is the medium. You could have sound in water. You could have sound traveling through like a solid wall, but you need a medium to be there in order to hear the sound. Because if there is no medium, these things, there's nothing to move. There's nothing to transfer the energy. Just like we said before, can you have a water wave without water? No. Well, can you have sound without some kind of medium? No. So sound is a longitudinal wave. Sound is a longitudinal wave because the particles of the medium vibrate parallel to the wave motion. And that's going to do it for our quick introduction to waves in general. Like I said, for the whole rest of the year, we're going to talk about cool applications of this and different types of waves and what else can we know about waves. So in the next lesson, we're going to talk about period and frequency. Then we do wave speed. And then one of my favorite things about waves is how waves interact with each other. What if you had a wave coming in and then another wave's going to come in over here, but this one's moving to the left and this wave is moving to the right? How will those waves interact with each other? It's called wave interference. And then you get into like some really cool stuff. So that's something to look forward to. And that's about it. Have a great day.